In 1977, humanity built a machine the size of a small car, pointed it at the outer planets, and gave it 5 years to live. Almost 50 years later, that machine is still out there, more than 15 billion miles from home, drifting through a region of space no human-made object had ever reached before it. And more than once, this aging, half-broken spacecraft has done things that made NASA's own engineers stop and stare at their screens. Because a machine running on 1970s technology should not be capable of the things Voyager 1 has pulled off. This isn't a story about aliens. It's stranger than that, because everything in it actually happened. Voyager 1 launched on September 5, 1977, riding a rare alignment of the outer planets that occurs only once every 176 years. A cosmic coincidence that let a single spacecraft visit multiple giant planets using each one's gravity as a slingshot to the next. Its twin, Voyager 2, had actually launched 16 days earlier, but Voyager 1 took a faster trajectory and overtook it. The original plan was almost modest by today's standards. Fly past Jupiter and Saturn, take some pictures, gather some data, and that would be that. Nobody involved in the mission seriously expected the spacecraft to still be transmitting information back to Earth 5 decades later. And yet, here we are. Just 13 days after launch, from more than 11 million kilometers away, Voyager 1 turned its camera around and captured something nobody had ever seen before: Earth and the Moon together, in a single frame, as two small points of light hanging in the dark. It was a strange, almost accidental preview of what this mission would eventually become. Not just a tour of distant worlds, but a slow, ongoing lesson in how small and fragile our own world actually is. When Voyager 1 reached Jupiter in March 1979, it didn't just take better pictures of a planet we already knew. It rewrote what that planet was. Jupiter went from a striped disk in a telescope to a churning, violent atmosphere of storms within storms, with the Great Red Spot confirmed as a rotating storm system larger than Earth itself. But the real shock came from one of Jupiter's moons. Before Voyager, most scientists expected Io to look like our own moon: old, cratered, quiet. Instead, Voyager 1 caught it in the act of erupting. Real volcanic plumes, blasting material hundreds of kilometers above the surface. It was the first time humanity had ever directly observed active volcanism anywhere beyond Earth, and it meant that this small, distant moon was one of the most geologically violent places in the entire solar system. Then came Europa, its icy surface crossed with strange fractures that hinted at something scientists hadn't seriously considered before. A hidden ocean, sealed under miles of ice, on a moon nobody had thought to look at twice. That single observation quietly reshaped the search for life beyond Earth. Instead of only looking at planets in a star's so-called habitable zone, scientists suddenly had to consider that a moon, warmed not by sunlight, but by the internal stress of a planet's gravity squeezing and flexing it, could harbor liquid water of its own. A possibility nobody had seriously planned for before Voyager 1 flew past. After Jupiter, Voyager 1 used the planet's gravity as a slingshot towards Saturn, arriving in November 1980. Saturn's rings, which had always looked smooth and simple from Earth, dissolved on closer inspection into thousands of individual ringlets, gaps, and braided structures far more intricate than anyone had modeled. And at Saturn's largest moon, Titan, Voyager 1 found something remarkable: an atmosphere so thick and nitrogen-rich that its surface was completely hidden from view, with conditions cold enough that methane could exist as a solid, liquid, and gas, essentially playing the same role there that water plays on Earth. That close flyby of Titan came at a cost. Saturn's gravity bent Voyager 1's path sharply out of the plane of the solar system, permanently ending any chance of visiting Uranus or Neptune. From that moment, Voyager 1 stopped being a planetary tourist. It became something else entirely, a one-way traveler heading for the edge of everything we understood. It's worth pausing on just how much this one mission overturned in the space of about 18 months. Before Voyager 1, the outer solar system existed mostly as a set of educated guesses. models built from faint light gathered through Earth-based telescopes, decades apart, with almost no way to check whether any of it was accurate. After Voyager 1, Jupiter and Saturn stopped being abstractions. They became places with weather, geology, and internal histories written across their surfaces. Places, it turned out, that behaved nothing like the calm, static worlds astronomers had assumed they were. For more than 3 decades after leaving Saturn behind, Voyager 1 kept moving outward in relative silence, its cameras shut off to conserve power, its instruments quietly recording the increasingly thin, faint edge of the Sun's influence. Scientists assumed that edge, the heliopause, where the solar wind gives way to true interstellar space, would be a slow, gradual transition. A gentle fading, like a room slowly getting darker. That is not what Voyager 1 found. On August 25, 2012, its instruments recorded a sudden, sharp drop in solar particles, and in the same moment, a spike in high-energy particles arriving from deep space. Not a gradient, not a slow fade. An abrupt boundary, almost like the spacecraft had crossed through an invisible membrane. Voyager 1 had become the first human-made object to physically leave the solar system and enter interstellar space, the space between the stars. And interstellar space did not turn out to be empty or silent the way many expected. From more than 24 billion kilometers away, Voyager 1 picked up a faint, persistent signal. Plasma waves in the interstellar medium, humming at a consistent frequency for nearly 3 years. Some scientists described it, almost poetically, as the sound of the galaxy itself. It let researchers measure the density of interstellar space directly for the first time, turning something inaudible into a genuine scientific instrument. At the same time, Voyager 1's data revealed that the magnetic field just outside our solar system was 2 to 3 times stronger than any model had predicted, pressing in on the heliosphere with far more force than anyone expected. It turns out our entire solar system sits inside a kind of compressed bubble, squeezed by the surrounding galaxy. A detail we simply had no way of knowing until a 50-year-old spacecraft flew straight through the boundary and reported back. Voyager 1's data also helped confirm that our Sun sits inside something called the local bubble, a cavity roughly 1,000 light-years wide, carved out over millions of years by a series of ancient supernova explosions. That bubble is thought to shield our solar system from a large amount of interstellar dust and radiation that would otherwise be reaching us directly. In other words, one of the reasons Earth has stayed as stable and livable as it has may partly come down to the accident of which particular patch of the galaxy our star happens to sit in, something we only understood properly because Voyager 1 was there to measure it firsthand. By 2022, Voyager 1 had already outlived every reasonable expectation placed on it by more than 4 decades. Its power output was fading year over year as its plutonium fuel slowly decayed, and engineers had been shutting down instrument after instrument just to keep the essentials alive. That's normal, expected, manageable decline for a machine this old. What happened next wasn't. Engineers monitoring Voyager 1's telemetry began noticing something that made no sense. The spacecraft's own systems reported that its antenna was pointed in the wrong direction, an orientation that, if true, should have made communication with Earth essentially impossible. And yet, the actual signal being received on Earth stayed strong and clear the entire time. The spacecraft was, in effect, telling ground control it was looking one way, while clearly still looking the right way. For months, this went unexplained. It was eventually traced to a fault in one of the onboard computers, the Attitude, Articulation and Control System, generating garbled status reports, even while the spacecraft itself continued functioning correctly. It's a small, mundane explanation once you dig into it. But in the moment, for the engineers watching real data contradict itself in real time from a machine over 14 billion miles away, it was deeply unsettling. One team member later compared it to getting a phone call from someone whose caller ID said they were on the other side of the planet. The scarier moment came in November 2023. Voyager 1 suddenly stopped sending back anything meaningful. No science data, no coherent telemetry, just a repeating pattern of ones and zeros that didn't correspond to anything the spacecraft should have been producing. For a machine that had already defied its own expiration date by decades, this looked like the ending everyone had quietly been expecting. Engineers eventually traced the fault to a single corrupted chip inside the spacecraft's flight data subsystem, a piece of memory that had likely degraded after nearly 50 years of exposure to cosmic radiation, far from any possibility of physical repair. The fix required rewriting decades-old code and relocating it into whatever healthy memory remained on board, a procedure with essentially zero margin for error, on hardware nobody currently working at NASA had originally built. And here's the part that makes the fix itself feel almost unbelievable. Every single command sent to Voyager 1 takes about 22.5 hours to arrive, and any response takes another 22.5 hours to come back. A single attempt to fix the problem consumed nearly 2 full days of waiting, with no way to know if it had worked until the reply finally arrived. On April 20th, 2024, after that agonizing wait, Voyager 1 spoke again. Clear, coherent data, flowing correctly for the first time in 5 months. Voyager 2 had faced its own near-death moment just months earlier, when a routine command accidentally tilted its antenna 2 degrees away from Earth, silencing it until a powerful signal from a tracking station in Australia managed to restore contact 37 hours later. What makes all of this land differently is just how little Voyager 1 has to work with. Its onboard computer carries less memory in total than a single low-resolution photo on a modern phone. Its data, for decades, was recorded onto magnetic tape, a format that's essentially a museum piece today. Its radio transmitter broadcasts back to Earth at roughly 22 watts of power, about the same as the light bulb inside a refrigerator, and that faint signal is still detectable across more than 15 billion miles of empty space. All of it is powered by radioisotope thermoelectric generators, quietly converting the heat from decaying plutonium into electricity, losing a small amount of output every single year, with engineers shutting down one non-essential instrument after another just to keep the spacecraft's most critical systems breathing. And it just keeps going. Not because it was built better than anything else humanity has ever launched, but because a small group of engineers has spent nearly 50 years finding new ways to keep an aging, dying machine alive across a gap of light hours, using tools and knowledge that in some cases predate the internet itself. Some of the original engineers who worked on Voyager in the 1970s have since retired or passed away, which means the current team keeping it alive is often relying on decades-old technical manuals, hand-annotated schematics, and institutional memory passed down rather than any kind of modern documentation. Every fix has to account for the fact that nobody can simply plug in a diagnostic tool and read an error code. They're troubleshooting a computer from the Ford administration, using instructions written by people who assumed it would have stopped working decades ago, all while working around a communication delay that turns every single test into a 2-day round trip. Bolted to the side of Voyager 1 is something that has nothing to do with science at all. The Golden Record, a phonograph disc containing greetings in 55 languages, natural sounds from Earth, and a curated selection of human music sealed with instructions for how to play it, on the extremely unlikely chance that something, someday, finds it. Nobody who built it expected it would ever actually be discovered. The record wasn't really made for an alien audience. It was made for us, a way of saying, formally and permanently, that we were here, that we looked outward, and that we tried to describe ourselves honestly before sending a piece of ourselves into the dark. The committee behind it, led by astronomer Carl Sagan, spent months debating exactly what belonged on a disk meant to represent the entirety of human experience to an audience that might not exist, using a shared language that might not exist either. They landed on images encoded as analog data, spoken greetings, natural sounds like wind and thunder and animal calls, and 90 minutes of music spanning cultures and centuries. Everything from classical composition to field recordings, deliberately chosen to avoid representing any single perspective as the definitive one. It's one of the only parts of the entire mission that wasn't designed to answer a scientific question. It was designed to answer a much stranger one. If you had one disk to describe your species to whatever might eventually find it, what would you actually choose to say? That's arguably the most human part of the entire mission. A machine built to study gas giants ended up carrying a message about who we are into a place where it will likely drift, unopened, for longer than our own civilization has existed. Voyager 1 isn't finished yet. It's still transmitting, still being tracked, still occasionally surprising the small team at NASA that keeps it alive year after year on a shrinking power budget. It's currently heading toward the Oort cloud, the distant shell of icy debris that marks the true outer edge of our solar system's gravitational influence, a region it won't even reach for another 300 years, and won't fully pass through for roughly 30,000 years after that. Long after its radio signal finally goes quiet for good, and engineers now estimate that could happen sometime in the next few years, as power keeps declining, Voyager 1 will keep drifting, silent, unpowered, carrying its golden record through the space between stars, on a journey with no destination, and most likely, no one waiting on the other end. That's the real story here, not a secret transmission, just a 50-year-old machine, built with less computing power than a musical greeting card that keeps finding new ways to surprise the people who built it, and a small, stubborn record of humanity, still moving outward, long after everyone who built it assumed it would have gone silent. If stories like this, real anomalies, real spacecraft, real mysteries that don't need any embellishment, are why you're here, subscribe so you don't miss the next one. And let us know in the comments. What part of Voyager 1's real story surprised you the most?